Okay, so we start the sum of the algebraic structure like group. We start with the groupoid, then we will move to the algebraic structure group. So, before that let us just define what do we mean by binary composition. Or binary operation. Okay. So, binary let A be an non-empty set of element. Then we defined a function f from A cross A to A. Okay, it could be okay, A cross A to A. So, basically we take an element from A, another element from A, and we apply this. So, we take an element from the Cartesian product A cross A, and then we apply this function. This function is basically function from the Cartesian product to this. Then this is, if this is belongs to A, then it is called closure property. So, basically, but binary composition means this type of function is called binary operator or binary composition. This is called binary operation. Okay. So, like plus, if we take say A to be natural number set. So, if we take A B from this, then if we define plus, then this is basically, this will also give us a natural number. If we add two natural number, so plus is a binary composition or binary operation. Okay. Now, this is on a set A. So, basically we take two elements from A and then we compose this with the operators this f, or sometimes we denote this by in general star. So, we take, this is our A set, we take two elements from this A B. Now, we compose this by a operator star, which is basically function from take two elements from A, and then it may give a element in A or may not. If it is giving an element in A, then we call this is a closure operator. So, like addition on natural numbers. So, suppose A is n, then addition is a closure. So, like if we have a natural number set and if we take A plus B, then this is also belongs to n. So, addition. So, this addition is closure. This is called closure property. So, what is closure property? So, if we have an operator A cross on A by binary operator on A, so it will be called closure if A star B belongs to A for all A B. Then this is called, then the operator is called, then the operation is called, this binary operation is called closure operation, or it is satisfying the closure property. Now, for example, this plus is closure on this set n, but subtraction is not closure, because if you take two natural numbers, say 1 and 2, sorry 1 and 2, two natural number. Now, 1 minus 2 is basically minus 1, which does not belongs to n. This is an integer. So, this minus is this subtracted, this is not a closure operator on n, but it is closure on z. If you take z as our set, then minus is also a closure on z. Okay. So, this is the definition of a closure operator. So, a operator is need not be always closure on a set. Okay, now we say a operator is commutative. This is the definition. Commutative. This is so suppose we have a operator star on the set A. So, that means it takes two elements from A and it operates the star and it gives an element. If it is closer, that element will belongs to A, otherwise it need not belongs to A. But for commutative we need this property, A star B must be B star A, and this is true for all A B. Okay. So, A star B must be B star A, and this is true for all A B. So, if this is satisfied, then we call star is commutative. Similarly, we can define, like for example, addition. If we take A to be Z or N, now if we define A plus B, now this is the real number addition. So, A plus B we know is same as B plus A. So, like 2 plus 5 is basically 5 plus 2. So, this plus is commutative. But minus is not commutative, subtraction is not commutative, because 2 minus 3 is not same as 3 minus 2. 2 minus 3 is minus 1 and 3 minus 2 is 1. So, this minus operator, subtraction operator is not commutative. So, commutative also called abelian. Commutative property is also called abelian property. Okay. Now, we define associativity when we call a operator is associativity property, having associativity property. So, let us just define that. So, again suppose you have a set A and you have an operator on this set. So, this is basically a function from A cross A to maybe on A. If it is on A, then it is a closure property. So, now we call this is associativity if we take three elements A, B, C, A star, B star, C is equal to A star, B star, C. Now, for this we need to have this property to be closure, because if it is not closure, then A star, because this operator is defined on A cross A, I mean to A if it is closure, but if it is not closure, then we are defining B star C. Now, B star C has to belongs to A, because again, so B star C is an element of A, then only we can operate. So, this is some Z. So, A star Z, some D. Again similarly, this is some say E star C. So, that is why we for this associativity checking, I think we need to take this to be closure, otherwise this has no meaning, because when we do the B star C, this has to be a member in A, then only we can again operate with the other member of capital A. So, that element must be same as this one. So, and this must be true for all A B C belongs to this. So, this is the property of associativity. Now, so now we will take some example. So, plus is associative operation. So, if we define this plus, say, so if we define this, so suppose some of the example. So, suppose we define R set of real number and we have a operator plus. Now, we know the two plus is commutative because a plus b is equal to b plus c. So, this is commutative. Now, also it is associativity because a plus b plus c is same as a plus b plus c. We can take any three real number, fraction also will okay, 5 plus 3 plus 9 is equal to 5 plus 3 plus 9. So, this plus is having associated, this is coming from the real number, property of real number. So, this is true for all A, B, C. Okay, so, this is plus is both commutative and associative. Similarly, if we have say dot multiplication, real number multiplication. Okay. So, this is also because A dot B is equal to B dot A. And it is also associativity is also there, A dot B dot C is equal to A dot B dot C. Okay. So, this is also associativity. Now, if you take the matrices, set of matrices, say 2 by 2 matrices M to R, where numbers are coming from real numbers. So, A, B, C, D. So, this set, this is A, B, C, D belongs to R. This set is defined as all 2 by 2 matrices where elements are coming from real number. Now, on this matrix set, if we define plus, we know how to define plus. We take x1, y1, z1, w1 plus, this is the matrix addition x2, y2, z2, w2. Then this is basically x1 plus x2, y1 plus y2, z1 plus z2, w1 plus w2. This is how we define the matrix addition. This is plus. Now, these are all plus of real number plus, because these entries are coming from the real number. So, this will give us a this we can show because of this, these are real number addition. So, this is commutative, also we can show this is a associative. Now, if we take the into, that means matrix multiplication, say how to define matrix multiplication, say x1, x2, x3, x4 into y1, y2, y3, y4. So, matrix multiplication is basically, this will also give us a 2 by 2 matrix. Now, this so this is basically x1 y1 plus x2 y3, and then here x1 y2 plus x2 y4, and then we have y1 x3 plus this into this x4 y3, then this into this x3 y2 plus x4 y4. This is how we define the product of two matrix. This will also give us a 2. Now, we know this is not a commutative operation. So, product is not commutative. We can easily check that this matrix multiplication, this is not commutative. Okay. Now, we can take another example on say set. Suppose we consider suppose we have a set S, non-empty set. We have a non-empty set S. Now, we consider the power set, pow of S. This is basically set of all possible subset of S, set of all possible subsets of S, which include the null set also and the set itself. Okay. Now, if we define the, now this is our set A, on which we would like to have a operation like. So, we define the operation union and intersection. First of all, union on the pow set. So, union, this is also a closure operation. So, union is a, if we take A cross A, if we take two subsets, if you do the union, this will give us a subset, and intersection also, if we take two subsets of S and if we do the intersection, it will give us a subset of S. Okay. Now, how to show? So, is this commutative? Like yeah. So, these are all this is commutative, because we know the union operation like A union B is basically B union A. Also, intersection A intersection B is equal to B intersection. So, these two are commutative operation, and associativity, yes, this is also associativity is there, because A union B union C we have proved, I think, in the class of set theory. A union B, then whole union C. Similarly, for intersection, A intersection B intersection C is basically A intersection B intersection C. So, these two operations are both commutative and the associativity. Okay. Now, we will take another operation, which is basically finite on the finite set. This is basically Zn. Zn means let n be a natural number. What we are doing? We are just taking this integer set and we are considering each integer, we are taking mod n. Okay. That means, we take two AB, two integer, and we are defining a relation, the modulo n relation, if and only if. So, A is congruent to B mod n, if and only if A mod n is same as B mod n. So, that means, we take two integer and we try to divide them both try to divide them by n. Now, if they are giving us the same residue, then they are in the same class. So, that means, A minus B is divisible by n. So, n divides A minus B. So, that is the idea. So, then they are same class, and that class will be our this Zn basically. So, this is 0 class, 1 class, because if we divide any integer by n, so remainder will be either 0, 1, 2 up to n minus 1, 2, 3 dot 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 up to n minus 1. So, these are the all points like n, 2n, 3n, minus n, okay, because these are the points which are, if we divide by n, they will be just give the remainder 0, and these are the point which is n plus 1, 2n plus 1 like this. Okay. Now, this set Zn, on this set we can define the operation like plus and multiplication, like if you take n is equal to say 5 for simplicity. So, we are in Z 5. Z 5 means 0, 1, 2, 3, 4. This is our Z 5. Okay. Now, how we define an operation like plus? Plus means if you take any two element A B, A plus B is basically we are defining as A plus B mod n. So, here n is 5 mod 5, and this will give us another class. Okay. So, this we can just, since there are finite number of element, we can just have a table on this, say 0, 1, 2, 3, 4, then 0. We want to see whether this plus is closer or not. Okay. And also we want to see this is a commutative or not. 2, 3, 4. Okay. So, now with 0, if we add it up, it will give us all this, because 0 plus 2 is 2. Now, with 1, 0 plus 1 is 1, 0, 1 plus 1 is 2, this is 3, this is 4, then we have 1 plus 4 is 5. So, 5 mod 5 is 0. Okay. Then this is 2, this is 3, this is 4, then again this is 0, then this is 1. So, then this is 3, this is 4, this is 0, this is 1, this is 2, like this. So, the last one is this is 4, this is 0, 1, 2, 3. Okay. So, this we can verify easily that this is a closure property is satisfying, because all the elements over here are coming from Z 5. So, for simplicity we can just remove these brackets and we can just have this 1 0 1 2 3 4, but anyway this is okay. So, this is all the elements. Now, is this commutative? This is we can check, this is easily we can check commutative. We can take any two number, say 1 2. So, this is giving us 3, which is same as 2 1, which is also this class. So, this is a commutative, and also we can verify this is the associativity also. So, this plus commutative and associativity. Okay. So, again instead of plus we can just define a into, like, so this will be A into B mod 5. So, if you do that, then it will change like this. So, if you multiply this, all will be 0 0. Now, with 1 this will be 0, this will be 1, this will be 2, this will be 3, 4 with 2. So, this will be 0 for all. So, with 2 this will be 2 and this will be 4, 2 into 2 4, 4 mod, this is okay. So, this is 4 and this will be, so 2 into 6, 6 mod 5 is 1 and this is 8, 8 mod 5 is 3. Then come here. So, this is 0, this is 3, this is 6, 6 mod 5 is 1 and then 3 into 6 9, 9 mod 5 is basically 4 and then 12, 12 mod 5 is 2, then 4, this is 0, this is 4 and this one is 8, 8 mod 5 is 3 and this is 12 12 mod 5 is 2 and this is again 16 mod 5 is 1. Okay. So, this is the way how we define this. Now, is this commutative? We can check that if we take this 2 3 is giving us 1 and this 2 3 is giving us 1. So, it is commutative. So, this is one example where we have this. This is the over the finite set. So, if the operator is over the finite set, we can just have a table and then we can check whether they are commutative or they are associativity or not. So, in the next class we will start some algebraic structure based on this operator and then we will slowly start the concept of group. Basically, we start with the groupoid, then we slowly go to the group. Thank you.